section 8.4. And does it act like my audio is okay? Well, it looks like my audio is okay, so I don't know. We're just going with it. All right, but anyway, we had a couple things. First of all, we said we had a theorem. An infinite series of positive terms is convergent if and only if, so both ways, the sequence of partial sums has an upper bound. All right, so if the sequence of partial sums has an upper bound, then the series is going to be convergent. So we looked at an example of that last week with 1 over n factorial, and then we can kind of do some comparison tests. So that's another nice theorem that we have, proven fact. So ultimately, we're trying to get some other tools to figure out if series are convergent or divergent. So we could have all kinds of different looks on what a series is. Anyway, so we're gonna let they use A sub n instead of A sub n's and B sub n's, they're using U sub n's and V sub n's and W sub n's. I don't really like that, but I guess I'm gonna match the book because C a lot of times is a constant. Since there's 3 of them, they're using U, V, and W instead of A, B, and C, since C is typically a constant. All right, so we're going to let this infinite series n equals 1 to infinity of U sub n be a series of positive terms. All right, so basically the sequence of partial sums is all going to be positive as well, right? Because if you're adding up a bunch of positive terms, it's going to stay positive no matter how far out you go, right? So first and foremost, if we have a series of positive terms, well, so we got this one. I'm also going to have n equals 1 to infinity of V sub n, V, so that's a V. So I put a leg on it, so you know. Anyway, this is also going to be a series of positive terms. All right, and basically, if the sum I equals 1 to n of V sub n converges, so that's a series of positive term. If that converges, and we have U sub n is less than or equal to V sub n for all positive natural numbers n, then what are we going to know about the series from 1 to infinity of U sub n? What do you think that's going to do? It's going to converge. Okay. So what this is, basically, if we can compare it to something that we know converges, and we can show that that the U sub n's are less than or equal to V sub n's the whole time, and the series from 1 to infinity of V sub n converges, then the series from 1 to infinity of U sub n is also going to converge. So this is what we call the comparison test. And as you know, it doesn't take long to get awkward in with some of these setups of sequences and series, right? So basically, we get an awkward one, but we can compare it and show less than or equal. If we can show that this is true, then we're good. Okay, as far as that goes. Now we can also use it the other way. So here's let me use another part of this. So part 2, sorry. If now we could say they use a third term. We don't really have to. But I'm just gonna use the same one. So if the series from 1 to n equals 1 to infinity of v sub n diverges, okay, so if it diverges, and what do you think we're going to have happen? If u sub n is greater than or equal to v sub n, so now the u sub n's are bigger all along the way, what do you think is going to happen? Then the infinite series from 1 to infinity of u sub n is going to do what? It's going to diverge, okay? Which is exactly what, that's what the theorems say, but that makes sense because basically if you're going to be bigger along the way, so in this case, the u sub n is bigger than the v sub n's, and if this one diverges, the sum infinite series from 1 to infinity of v sub n, if that diverges and all the sequence of terms is bigger at every single spot, then you know that the other one's going to diverge as well because that would just make sense, right? So let's trash that, start over. They give a proof in there. I'm not going to go through that proof. Let me see if I kind of want to get some results here. All right, I'm going to look at my own example here. Ooh, this is in red. This will get you fired up. So we want to look at the infinite series from n equals 1 to infinity of 1/2 to the n squared. Okay, that makes sense. 1/2 to the n squared power. And the question is this convergent? Okay, well, once again, we haven't had a series like that, but we could actually, let's list it out and kind of see what's going on with this, shall we? So I didn't really need to rewrite this again, but what's that equal? What's the first? If equals 1, we get 1/2, right? And then we're going to add, if n equals 2, it's 1/2 to the 4th power, right? Which is what? 1 over 2 to the 4th, which is 1/16, right? If n is 3, 3 squared is 9, 1 over 2 to the 9th. Well, everybody knows that 2 to the 10th is 1,024. So it's 512. So this would be 1 over 512, isn't it? But anyway, so, if we wanted to write this out with a different look, what would it be? It'd be 1 over 2 to the 1st plus 1 over 2 to the 4th plus 1 over 2 to the 9th. And what would the next one be? 1 over 2 to the 4 squared is 16, right? Right? Everybody good with that? Plus, etc. Keep going. Okay. Now, first of all, one of our quick tests was what? Is it even possible to be convergent? What would have to be the case? Well, that's only if it's a geometric sequence, right? Is this a geometric sequence? Not really. Geometric sequence, you get to the next successive term by multiplying by a fixed number, right? So this is not, well, this is a series anyway, but looking at the sequence of partial terms. But as far as, is this a geometric sequence, 1/2, 1/16, 1/512? No, because I multiply by 1 over 2 cubed to get to the next term. Like if we're looking at this as a sequence, 1/2, 1/16, 1/256, I multiply by 1 over 2 to the 8th here. No. No, I don't. 2 cubed, which is 8. 1 over 2 cubed there, but I got to multiply by 1 over 2 to the 5th here. Okay, so it's not a geometric sequence. That would have made it nice if we could recognize it like that. It kind of looks like one though, right? And that might be a hint for what we're going to need to do. But what do we need? This as a sequence in and of itself has to have a limit of what? So the limit as n goes to infinity of 1/2 to the n squared, or better yet, 1 over 2 to the n squared. What's that equal? As n goes to infinity, what's 1 over 2n squared? 0. So is it possible? It is possible to be convergent. Now, does that guarantee victory? It does not guarantee victory, right? So anyway, so once again, we could do all kinds of different things here, looking for patterns and things like that. But obviously, I'm doing this right after the comparison test because we want to try and compare this with something that we know. Okay, well, what is a something that we know? What would it look like if it was geometric? Be like 1/2 to like the n power, right? Or k power, something like that. So like, but we have n squared there, so it's a little bit different. But let's look at each term along the way. So I'm going to use a different color here. We use purple because purple's lucky, right? Are you feeling lucky? Of course you are. If I have 1 to infinity of 1/2 to the nth power, is that a geometric sequence? Geometric series, excuse me, which means that this part in here is a geometric sequence. Is that true? This is a geometric sequence, right? This is a geometric sequence with r equal to what? This r equals 1/2, and which is less than 1, so therefore what? This converges, so therefore this converges. So it might think, well, it has a look like this, so it's not to the nth power, it's to the n squared power, which is, so the one above is not a geometric series because that's not a geometric sequence in there. However, it looks very similar to one that actually does converge. So what's your thought process? The thought process would be, well, I think that might converge, right? So could I use the comparison test of the top one with the bottom one? And so what would we need to show? If we're going to use the comparison test and we know the purple one on bottom converges, what do we need to know about each term along the way? That'd be less. That the sequence of partial sums of the top one in red would be less than, or blue, red or blue, whatever, would be less than the bottom one, or basically the sequence terms for the geometric sequence in black above is less than this geometric sequence down here. So anyway, what do we know? We know that, well, let's list out this one down here in purple. So what does this equal? This equals, if I plug in 1, what do we get? 1/2, right? Plus 1/4 plus 1/8 plus 1/16. Therefore, as we're going here, you know, this is a geometric series because this is a geometric sequence right there, right? 1/2, comma 1/4, comma 1/8, comma 1/16, etc. Right? And we're multiplying by 1/2 to get to the next one, to the next successive term, right? Okay, so what do we know here? Let's just look at the first one. Well, and then I guess I'll use black here, but here's 1/2. The first one here is 1/2. Is 1/2 less than or equal to 1/2? Yes. Is 1/16 less than or equal to 1/4? Yes. Is 1 over 512 less than or equal to 1/8? Yes. So let's go out to the nth term. I'm going to go back to red. So what's the nth term for this one? It'd be 1 over 2 to the n squared, right? We're in a some number bigger than 1. What would it be down here? I'll use purple on the purple one. Oh, by the way, and then plus, and it keeps going, right? Because we're going to infinity. So let's go down to the purple one. What's the nth one? It's 1 over 2 to the nth, right? Plus, and then of course keep going to infinity. But then last but not least, we have 1 over 2 to the n squared compared to 1 over 2 to the n. Is it going to be more or less or equal when n is bigger than 1? It's less. So this is less than or equal. 1 over 2 to the n squared is less than or equal to 1 over 2 to the n for all n, right? So I showed it specifically for the first few, but in general, so I'm going to write that out. In general, 1 over 2 to the nth power is less than, and I'm strictly less than 1 over 2 to the n squared when n is bigger than or equal to 2, right? But what could I do? I could say 1 over 2n, 2 to the nth, not 2n, 2 to the nth is less than or equal to 1 over 2 to the n squared for all n, right? And this is just a different way of writing 1/2 quantity to the nth power is less than or equal to 1 over 2 quantity to the n squared power for all n. Right? Makes sense? So therefore, what can I say? Therefore, the infinite series n equals 1 to infinity of 1/2 to the n squared power converges by the comparison test. So we compared it with something that we know. So that's ultimately, and then read the examples in the book. The book didn't have one of those, right? That's why I like using something different, because you're reading those, right? But anyway, that one's going to converge. So we knew it had a chance because the limit of the sequence was 0, goes to 0, right? So we knew it had a chance, and then it kind of looked like a geometric sequence with a nice value of r being less than 1. Okay? All good with that? So that's a comparison test. All right, and then I got some other examples in there as well. And then there is a limit comparison test that I need to go over, and then there's a integral test, which is kind of nice too. Integral test. So this section is really full of quite a few tests, but nice theorems that result from that. So here's another theorem. This is the limit comparison test. So the first theorem that I did today was called the comparison test. That was a comparison test, right? This is a limit comparison test. Okay, so they have titles, which is nice. So the limit comparison test, so what do we have? We're going to have a couple assumptions here. We're going to let the sum n equals 1 to infinity of the u sub n and the sum n equals 1 to infinity of the v sub n. Now, we could use a sub n and b sub n. I think another reason that they don't use a sub n and b sub n is because those could be positive or negative terms, right? But what are we assuming here? These are a series of positive terms. So the plural of series is series, right? So these are series of positive terms. So I'm just going to put plus terms, positive terms for shorthand terms. All right. Then what do we have? What's our test? So what we're going to do, if the limit as n goes to infinity, we're going to look at u sub n over v sub n. Okay. So if this equals some constant C, which is also going to be greater than 0. That it has to be greater than 0 if it equals C, doesn't it? Why does that have to equal 0? Or I mean, be positive. I don't really need this. I don't really need to put that this constant is greater than 0, right? Because you have a positive term divided by a positive term. No matter how far out you are for n, since the above series are positive terms, right? Anyway, but anyway, then what do we know? So if the ratio of u sub n divided by v sub n is some positive constant, then both series either converge or both series diverge. So it doesn't guarantee victory on convergence, but it does guarantee that they either both converge or both diverge. So it's kind of nice. They both do the same thing. Okay? That good? And then we get a couple of other things that we get from this. If the limit is n goes to, so oh, by the way, for part 1, I should have put an if there. If that's the case, if the limit of the ratio. So on part 2, if the limit of the ratio is n goes to infinity of u sub n over v sub n equals 0, okay, and if the bottom one converges, so n equals 1 to infinity of v sub n converges, then what do we know? Then the infinite series n equals 1 to infinity of u sub n would also have to converge. Why do we know that? So let's talk about this one. If this limit is 0, which one is bigger as n gets bigger, the numerator or the denominator? So this ratio of u sub n divided by v sub n, which one's bigger if that limit goes to 0? The bottom one, the v sub n. That's why I circled it in purple, right? And if that one converges and is bigger as we go out to infinity, then the top one has to be smaller than something that converges. So that should make sense, right? As a theorem anyway, okay? And then we can use the other version of this. So I'm gonna use, can I just use a different color instead of rewriting it? I'm gonna use blue now. So this is part 3 is in blue. So part 3 says if the limit of that ratio instead of equaling 0 equals positive infinity. So it blows up. Okay. And if the bottom one diverges, okay, so it's not convergent, then what do we know about u sub n? That series. It's going to be divergent. So let's talk about why. Okay, in this case, if the limit of the ratio is positive infinity, what's happening along the way? U sub n is getting a lot bigger than v sub n as n gets bigger, right? So u sub n is much bigger as you go out. And if the infinite series from 1 to infinity of v sub n diverges, you know that the u sub n's are bigger as you're going, right? Then that means the infinite series from 1 to infinity of u sub n would also be divergent. Hopefully that makes sense without seeing an example. Okay, but that's the limit comparison test which I don't know if I got an example. I mean, obviously your evens are not going to be due tomorrow. You're welcome, Jordan, because we got a lot of stuff going on in this section. But I do want you to work odds over some of the stuff and make sure you're reading the examples. So I'm going to go on. I want to do the integral test. I at least want to expose you to that. This is on page 716. So here's a theorem. This is called the integral test. And this is kind of a nice theorem, this integral test. Let's see if I have time for an example. I'm not sure if I will. Otherwise, I'll pick that up tomorrow. So let f be a function. Obviously, I'm not going to write that out, but it's going to be continuous. So it's going to be continuous, decreasing, means going downhill left to right, and positive value, and positive values, height values, for all x's greater than or equal to 1. Now remember, we're only, the reason why do we start at 1? Because the natural numbers for series start with n equals 1 usually, right? They don't have to. We could start n equals 10 to infinity, but a lot of times we start at 1. The natural numbers start with 1. That's why we only care about x is greater than or equal to 1, okay? Then what do we have on this? Then we have the infinite series n equals 1 to infinity of f of n, right? Instead of f of x's, we're just going to hit the natural numbers along the way. Plug in n equals 1, 2, 3, etc. Not every single, we're not going to plug in pi, right? But anyway, what does this equal? This equals f of 1 plus f of 2 plus f of 3 plus f of n plus, you know, keep going forever, right? But anyway, this is convergent if the improper integral, definite integral from 1 to infinity, remember doing that for your last test? When that chapter 7, infinite integrals, infinite upper bound. If this exists, then this series, infinite series, is going to be convergent. But it's also divergent. I'll use a different color here, finish this up. This is divergent if the definite integral from 1 to infinity of f of x with respect to x does not exist, or equals actually plus infinity. So we can use an antiderivative that we learned back in chapter 7 with an infinite upper limit and use that as a test. But we have to have 3 things here. We have to have that f is continuous, so that means we'll be able to take the antiderivative of it. It's decreasing, going downhill, and it's positive valued all the way out, which means above the x-axis. So I ran out of time for examples. Assuming I don't get a chance to do that tonight, we'll do some more tomorrow, okay?